Let's get this show on the road. Hello, everyone. Hope you're well. Back at it again. Time for another Calc 2 class. Yay! Okay. So far, I had a class. I had a couple of, met a few students in office hours, and my internet hasn't given out on me yet. So it seems I'm cautiously optimistic that we will not have internet issues for this class. Okay, so let's actually keep the good track record here. Let's actually jump right in and begin the day. So this is what we started a couple classes ago, and it's called partial fractions. Well, partial fraction is just a way to take a big fraction and break it up into a lot of smaller fractions, which can be very convenient for calculus business. So if you want to do an integral and you have this big messy fraction that you want to do, find the integral of, breaking it up into smaller fractions is often going to be a lot easier to deal with. Partial fractions is a method to do that. And then integration by partial fractions is simply an integration technique where you first do partial fractions and then you integrate the resulting smaller fractions using some previous technique that you know about. So this was very useful because there are some situations in which the best way we know how to deal with it outside of partial fractions is to use a trig substitution, but we all know already that that's kind of annoying to use. So if you can avoid trig substitution, it's going to be good. So we went through the steps for how to actually perform a partial fraction decomposition, went through the 4 steps for that, and hopefully we understood that as well. We did a few examples of going through that kind of thing. And then we did a few examples where we actually applied this to integration. So here are some partial fractions examples, and did a lot of arithmetic for these. I didn't even check if these numbers are correct, because arithmetic. Okay, which is I'll talk about talk about arithmetic later. And here were our examples. So we did these, we did a bunch of these, and we left over with some more for you guys to do. So we're going to go through these. Hopefully you guys actually attempted them, and hopefully you guys actually started looking at your homework. That's also something I'll mention later. And let's just jump in. Nothing else to say. You guys take it away. Let me know what you did for this guy, and we can start moving on. All right, go. This is all you. This integral, cosine x divided by sine x times sine x minus 1 in the denominator. What do we have?
I broke up the fraction into a over sine x plus b over sine x minus 1.
Okay, so you looked at this. Like that?
Yeah.
And how did you finish up?
Is that correct?
Well, no, not really.
Oh.
So partial fractions is, remember, it's a way that we can break up rational functions. So having the trig functions here is an issue. Like, you're going to run into trouble trying to get the a and the b to coincide with a cosine. At least more trouble than you want to end up with. So having the trig functions there, yeah, so some suggestions are in the comments. You'd first do a regular substitution. And hopefully at this point, you'll see that u equals sine x would be the substitution you'll want to make. So your du is equal to cosine of x dx. And so your integral would actually just become 1 over u times u minus 1 du. So this is a rational function here. That's what I would actually want to use partial fractions on. And so, yeah, at this point, I break it up into something over u plus something over u minus 1. Or maybe the other way around. Sometimes it's nicer to put the guy, the smaller guy first. So u minus 1 plus something over u du. But if you put it the other way around, that's fine. Okay, so what are the tops? What goes on top of the u minus 1? Maybe tell me how you would even figure that out. Anyone? Bueller? It's 1 over u minus 1. Oh, by the way, be careful how you're typing that. So, because, you know, for our quizzes, sometimes we need to type the answers. You really need parentheses here, right? Because if you type 1 over u minus 1, the computer is going to interpret that as 1 over u and minus 1 separately. So you really need the parentheses. Yeah. Right. And we saw a shortcut for that last time. So this is actually going to be a minus sign here, minus 1 over u. And how we did that was to get the guy that's on top of here, to get this guy, I would cover up the u minus 1, plug in one. So I would just have 1 over u. I would cover up the u, plug in what would have made that 0, which in this case is u equals 0. And then I would end up with minus 1 as the answer. So use the cover up method to get to those answers relatively quickly. And at this point, it's easy to see that the integrals are going to be just logarithms. And now you plug in what the substitution was. We had u equals sine x. And so that is our answer here. So that is the integral of this guy. So hopefully that was fine. Hopefully that wasn't too bad. Let's actually look at the other ones. These a little bigger. And then let's move this guy over. Okay, so here was a guy. We actually did this guy before. We did this with a trig substitution. That was back here. I think this is guy. We made a definite integral, but we did a trig substitution, was a secant. We got blah, blah, blah. We got all this stuff, and we had to get a tangent squared, and we did all that, and then we blah, 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 blah. Then finally, we plug in the fundamental theorem of calculus, and we got that as the answer. So you can see what the trig substitution way would have looked like. However, for the trig substitution, when you got to this point, if it wasn't a definite integral, you'd have to draw the triangle and figure out what tangent theta is, what theta was, and that'll ultimately get you to the answer. So we've seen how to do this guy one way already. So now let's actually say I did not want to do trig sub. Okay, so I saw this and I'm like, you know what? There's an odd power of x somewhere. It's actually in the denominator. Get me another way to do this without doing a trig sub. Ideas.
You do u substitution.
Okay, what would you substitute?
U equals, yeah, u equals radical 1 plus x squared.
All right, let u equals the radical of 1 plus x squared. Or in other words, you would say u squared is equal to 1 plus x squared. So this means you can differentiate 2u du is equal to 2x dx, which you can reduce by 2 on both sides. And now you just actually go and you plug these guys in. So the radical of 1 plus x squared is just u. X.
It's going to be radical u squared minus 1.
Yeah, that's gonna be a little bit nasty though. So here's how I would actually do it. Realize here that this guy here is actually the radical of 1 plus x squared over x, but then I can multiply by x over x. And so this will actually be radical of 1 plus x squared over x squared times x, right? And so this x, so if I have this, so this x dx here is going to be the u du. And then the x squared here, I can rewrite that without the need of a radical. From this equation, I get that x squared is actually equal to u squared minus 1. So the x squared is u squared minus 1. And then my x dx becomes u du. So that's going to be my integral. In other words, this is the integral of u squared over u squared minus 1. And we've seen this guy before, or guys very similar to this. What I would do is I would subtract 1 and add 1 to that. And so this is going to really be 1 plus 1 over u squared minus 1. This side realize, well, this is u minus 1 times u plus 1. This I'd realize I can break up into 2 parts. So doing partial fractions here. And I do the cover up method, cover up the u minus 1, plug in 1, I would get a half. Cover up the u plus 1, plug in minus 1, I would get minus a half. And so this becomes u plus 1/2 ln of u minus 1 minus 1/2 ln of u plus 1 plus c. And then I plug in what my u was. So my u is actually the radical of 1 plus x squared plus 1/2 ln of, let's actually combine these, the radical of 1 plus x squared minus 1 divided by the radical of 1 plus x squared plus 1 plus c. And that's the answer there. Just by using a log rule here. So hopefully you guys got something similar to that. And that's it. So here, so you see something like this, you notice that there's an odd power of x. Now, of course, if the odd power is in the numerator, that's a lot easier to deal with. But once you have an odd power of x elsewhere, it means that substitution is going to kind of simplify things. However, if the odd power of x is in the denominator, normally you end up in a situation where an integration by parts is going to be useful. So here, u squared equals 1 plus x squared. I am able to rewrite the equation, the integral like this. That's just something that I can, first of all, I can't actually apply partial fractions methods using this because it's not a proper fraction. So I subtract 1 and add 1 so that this guy breaks down into that guy. And then I do a partial fractions on this part and can get through that relatively quickly by doing the cover up method. And then the integral is easy. Is it okay if you didn't use, you mean if you just wrote it out like this and then just substituted the radical here and here? That's what you mean? Like if you left it as 2 separate logs, then yeah, that's fine. They're exactly the same. I just wanted to make the answer a little shorter, because then if I start writing in this guy here, the line's going to get too long before I go off the side of the page. But yeah, leaving it spread out like this is fine in general. There are times when you're going to want to combine the logarithms. Like for example, if you're taking limits and you're approaching infinity, u is approaching infinity, then this situation would be an indeterminate form. But if you put it in this form, you can actually determine what the limit is in many situations. So they're definitely equal, but there are situations in which the compressed logarithm form is more convenient to use than the expanded logarithm form. Like an example that I just mentioned with limits, which I think next class we're going to start to see examples like that. All right, so that was that one using another method. So you see something like this, don't think you're stuck with trig substitution. In fact, if I saw something like that, I would prefer this method as opposed to a trig sub. But to each his own or her own. All right, what about this one? What'd you guys do here?
I factor out the denominator.
What does that factor into?
X plus 2, x minus 2, and x minus 1.
You factor this into x plus 2, x minus 2 times x plus 1?
No, x minus 1.
Really?
Yeah,
And that would give you what we had here? So this is x squared minus 4 times x minus 1. And we would, if we multiply it, we would get x cubed minus x squared minus 4x plus 4. We don't get that. So something is off here. That's not the factoring. So that doesn't actually work. And say here again, trick. You don't need partial fractions here. So I was just seeing who would pay attention to see that. Remember grasshoppers, remember your training. Okay, you don't actually need partial fractions here. Now, if I tell you that, can you figure out what you can do? The math problems give me trust issues. Yeah. Yeah, just like people, you know, you can't just blindly trust a math problem. Sometimes the thing that's the most obvious solution is actually not the best way. Tabular integration, someone's pulling out integration by parts. No, you're thinking too hard again. Think simpler. Why would you go all the way to integration by parts? Integration by parts is quote unquote step 4. Start from the beginning.
You know what, actually, how you would approach this problem?
Yeah.
You would actually try to do, like, think about the ln, you know? You would be like, you know, 1 over 3 ln absolute value of x cubed plus 3x minus 4 plus arbitrary constant c. You know, because want to know why? Because with 1 over 3 ln of absolute value, x cubed plus 3x minus 4, the derivative of x cubed plus 3x minus 4 is 3x squared plus 3 over x cubed plus 3x minus 4 multiplied by 1/3. You get, you know, x squared plus 1 over x cubed plus 3x minus 4. You don't need partial fractions. It's just simple, like, you know, logarithms.
Right.
Derivatives.
Now, does anyone, like, if you didn't see the logarithm, based on Jason's suggestion, because he said a couple things here. Right. Natalie got it. So you could see it Jason's way, or you can actually, let me give something a little bit more constructive for someone who probably wouldn't have seen right away that this is a logarithm. But yeah, if you do u equals x cubed plus 3x minus 4, notice that your du is going to be 3x squared plus 3 dx. And at this point, you might, well, how does that help? Well, notice that 3 is a common factor, which you can factor out. And at this point, you're like, look at this, gasp. Look at that. So this is actually a substitution problem. You didn't need partial fractions. It was a fake out, because sometimes you can actually. So here, what you'd realize is 1/3 du is going to be the numerator, x squared plus 1 dx. And so the integral just becomes 1/3 the integral of 1 over u. So it's actually just a regular u sub. Yes, some of you are thinking too hard. And this is the kind of problem where a student's going to be like, you know what? I'm going to do tabular method. And then they're going to take forever. And then they're going to come back and complain to me like, yo, Jhevon, that quiz was too long, man. You didn't give us enough time. And it's like, no, I gave you enough time. You're just thinking too hard. Like, I don't even know if tabular integration would have worked out. But even if it does, it's definitely going to be a lot longer and a lot more complicated than this right here. Think simply, grasshoppers. This is why I gave you the steps. And we'll talk about that a little bit later. This is why I gave you the steps. You see a random integral, there's a certain way you need to think about it. Is it a basic rule? Can I simplify it to be a basic rule? Can a substitution work? Right? That thought should enter your head before you start worrying about, well, tabular method or integration by parts or partial fractions or any of that. Every time you look at an integral, the first three things you think is it a basic rule? Can I simplify it to be a basic rule? Or can a substitution make my life easier, right? Now, if you had thought about that, you would immediately have seen, well, within a few seconds, you would have seen, yo, a u sub is actually going to work out here. Now, you just have to notice that you have to factor out the 3, which is a whole other thing. But you can see here that it actually works out to be a u sub by just going through the steps. And so in this case, we have 1/3 ln of x cubed plus 3x minus 4. Right. And of course, some people like Jason would actually see this like in hindsight. And based on a lot of Jason's responses, that he seems to be able to be good at deconstructing derivatives in his head. Not everyone is that good, or I shouldn't say that good. Not everyone's brain works that way, but this is a more constructive way. By the time you go to step 3 of the strategy that I gave you, then you'd realize, oh, the substitution is actually going to work. And then even if you don't see it backwards, you can literally construct the answer by going through a substitution. Is that a -4? Yes. Okay. So that's that one. Let's see. And to win an integration bee, you guys will actually, you're going to need way more knowledge than you learn in this class. But hey, it's the journey has to start somewhere. Okay. Here's a hint. Factor the denominator before beginning. Okay, so this actually goes back to something that I want to make sure you guys remember how to do. So let's actually talk about that. How do you factor x cubed minus 2x minus 4? Throwing it back to algebra class or pre-calc class, wherever you would have learned this. Did anyone figure out how to factor that guy? Because again, what you would think, is this a basic rule? No. Can I simplify to be a basic rule? Well, the simplify we don't really know, but you can also definitely eyeball it right away and realize that a u substitution would not work. The numerator has too many terms in it, and the numbers don't actually work out very nicely. So you'll probably spend a little bit longer on the simplification part. Can I simplify this to look like a basic rule? And once you start thinking of simplifying, what you want to think, when you want to simplify a fraction, we know how to do that. You factor the numerator and denominator and cancel common factors. So that's why I said, okay, start factoring the denominator before beginning, but you are going to have to remember how to factor the denominator. Does anyone remember how to actually do something like that? Factor that cubic. So I'm guessing the answer is no. I mean, everyone's so quiet. Okay, so going back to there was a point up here where I mentioned something. Let's see. It was in red. Here. Factor the denominator completely. Pretty much self-explanatory, but you need to remember all your factoring techniques, including the rational roots theorem. That's what we need here, rational roots theorem. Now that I said that, did anyone look that up? Do you remember how that works? Okay, so the rational roots theorem, if you have a polynomial, so if you have a polynomial like x to the n plus x to the n minus 1, going all the way down to a1x plus a0, then it says if there are rational roots, there might not be rational roots, but if there are, so this is theorem, the rational roots theorem. And it basically says, given a polynomial, if there are rational roots, then they are of the form plus or minus some factor of the constant term divided by some factor of the leading term. So this is the rational roots theorem. So this basically says, it tells you what are the possible roots of this guy. And by figuring out the roots, we can actually figure out how to factor something. So we have x cubed. So for example, for x cubed minus 2x minus 4, minus 2x minus 4, if we have rational roots, they look like plus or minus 1 over 1, so that's a factor of 4. Another factor of 4 is 2. Another factor of 4 is 4 itself. So rational roots in this situation, because there is a 1 in the main guy here, it's going to look like a factor of 4 divided by a factor of 1. And the factors of 4 are 1, 2, and 4. So the possible rational roots are, it's going to be either plus or minus 1, or it's going to be a plus or minus 2, or it's going to be a plus or minus 4. Now, of course, here, you'd start by plugging in the smallest numbers first. Your goal is to try to get a root, meaning an x value that you can plug into p of x and get 0. So notice that you can try p of, if you try p of 1, you'd realize that that's not going to give you 0. You can try p of minus 1 and realize that's not going to give you 0 either. What about p of 2? That one's not so clear. Let's actually write that out. P of 2 is going to give you 8 minus 4 minus 4. That's 0. So this guy tells you x equals 2 is a root. Now there's another theorem called the factor theorem that tells you that this means that x minus 2 is a factor. Meaning when you factor this polynomial, x minus 2 is going to be one of the factors. And so what that means is that I can divide the x minus 2 into this guy, which is another reason why we need to remember polynomial long division. course, remember, we have to account for all powers counting down. So I need to leave space for the squared term here. Now we're going to do the long division. X into x cubed goes x squared times this goes x cubed, x squared times the -2 goes -2x squared. Subtract this guy from the guy above. The x cubes kill each other. I would be left over with 2x squared. Then I take x into the 2x squared. I would get plus 2x. Take the plus 2x and multiply everybody on the left. I would get 2x squared minus 4x. Subtract that from the line above. So the 2x squares will kill each other. And I would have the minus 2x plus 4x. So that would give me a 2x here. Then I'd say x into that 2x goes plus 2. 2 times this, 2 times x is this, 2 times that is minus 4. Subtract this from the line above. So it's 4 plus 4, and I end up with 0 here, which we should. We should get 0. Since the x minus 2 is a factor. So basically what that means is the original guy, this guy here, is equal to the numerator here, which we call the quotient, x squared plus 2x plus 2, times the divisor, x minus 2. So that's how you'd factor that, rational roots theorem. And yes, the process is lengthy, but in general, you should be able to get through this relatively quickly. A problem like this would be one of the longer integration problems. So bringing that back here, this we would get is equal to the integral. Now I see how the denominator factors. It's x minus 2 times x squared plus 2x plus 2. The numerator is a quadratic, and that also factors. That's going to factor into x minus 2 times x plus 1. Now you're going to notice that these guys cancel. So you're going to get the integral of x plus 1 over x squared plus 2x plus 2. And so now this is a new integral. So what do? Go back to the basics. Step 1, is it a basic rule? No. Step 2, can I simplify to look like a basic rule? No, I don't really see. Step 3, can a substitution work? Well, let's see. U equals x squared plus 2x plus 2 would probably be the substitution. Your du would be 2x plus 2 dx. Factor out the 2. That's that. Gasp audibly. You can do that now because you're not in person. You won't disturb everybody else in the class. That's that there. So that tells you that this integral is actually 1/2 the integral of 1 over u du. And so this gives you 1/2 ln of u, of absolute value of u. And this is 1/2 ln of the guy x, I forgot what it was, x squared plus 2x plus 2. X squared plus 2x plus 2. And that is actually the integral. Oh, okay, great. You did that part in your head. Nice. So Natalie's like exclaiming at this point, and I'm not even sure what she's exclaiming about, but double exclamation point. I don't know if that's good or bad, but hopefully that was, and I'm assuming that we've seen something like this before. I mean, you would have done this in pre-calc. At least if you did pre-calc at City College, you would have done this guy, the rational roots theorem, learning how to factor cubics and larger things where an obvious factoring strategy won't work. What you try to do is you guess numbers to plug into the polynomial based on the rational roots theorem. Once you realize you find a root, then it means x minus that number is going to be a factor, and then you try to do a long division. You get 0, and that tells you that this guy under here factors into this guy here times that guy there. Oh, you just learned the rational roots theorem right now? That's strange, but it's normally taught in a pre-calc class, so that's now a thing. But hey, if you're just learning it now, that's the rational roots theorem. Helps you to factor bigger things. If you want more examples on that, you can watch my 195 lectures. That Math 195 is pre-calc at City College. Okay, and I believe that was our last example here. Yeah, so we got through a bunch of things. So that is integration by partial fractions. You can deal with a lot of random guys, especially if you can rewrite them using a substitution or otherwise as some rational function where the denominator factors and the numerator is of smaller degree than the denominator. Yeah, I also have Calc 1 lectures. That's called Math 201. And the last time I recorded that was fall 2019, which is the version you want to watch because the 201 syllabus changed recently, and the sequence I recorded in fall 2019 is the new version of 201. I have another series of lectures for 201, but they're from the old syllabus. So not everything is there. All right. That kind of wraps it up. Now, normally during the regular semester, I teach another technique called the Weierstrass Substitution, which is very cool. It's also something that I didn't learn in Calc 2, but it's actually actually a fundamental technique. You might be wondering, I don't know if anyone was wondering, the proverbial student. We looked at trig substitution, which means basically you go from a situation where you did not have trig functions and you introduce a trig function to get the integral to be easier. It turns out that sometimes the inverse operation is true. You might have trig functions in your integral, but you don't want them there. And so what you do is you substitute an inverse trig function to rewrite it without a trig function. Okay, so that is called a Weierstrass substitution or an inverse trig substitution or an inverse tangent substitution because you actually substitute an inverse tangent. Okay, so I'm not going to cover that with you guys though. I did cover that in the regular semester. You can watch the links here if you're interested in that. But for the summer is already kind of cramped. So anything that was kind of optional, I'm not really going to cover here. So yeah, I know, Kayla, but you can, virtual Jhevon will teach you if you go to these links that I put in here. I'll copy this in the notes here. So the thing is, the Weierstrass substitution is not officially in our syllabus, but I taught my class the Weierstrass substitution in the spring because I want my class to be better than all the other Calc 2 classes, and I want them to know more than all the other Calc 2 classes. It's kind of like, you know, when you're a parent, you want your kids to have an advantage over other people. So I taught them an extra technique because it's a fundamental technique and it's going to be very useful in the future. And even though it wasn't in the official syllabus, I thought they should know about it. But for the summer, like I said, things are already kind of crammed. We have 4 classes per week and it's already kind of crazy. So I don't really want to talk about this yet, especially we're never really going to have to use it. I might throw it in as a bonus problem on a quiz or two, but I'm not going to officially test you guys on this during the summer. If you are interested in how that works, what it would actually look like, you can go to these 2 links here. I will link you guys to that in a bit. But the Weierstrass substitution is essentially an inverse trig substitution. It literally goes in the opposite direction of a trig substitution. And it's named after a mathematician, a German mathematician called Weierstrass. Okay, so I just thought I'd throw that out there if you're interested checking it out, but the summer is already kind of crammed. I don't really want to cram in a lot of optional material, even though it's very fundamental and it's very useful. So what I think here, yeah, we're pretty much going to wrap up with this. What I want to wrap up today's class with is integration strategy. So 2020. Okay. So we have pretty much covered, we're not fully done with integration, but we've pretty much covered every technique that I'm going to teach you for integration so far, except, you know, the Weierstrass substitution would be the other technique, right? Now, in future classes, you are going to learn, and if you wanted to go to an integration bee and compete, you would have to learn many more strategies for doing integrals. However, all of those strategies ultimately will depend on the techniques that I showed you just now, right? So the techniques that I just showed you, these are the fundamental, the foundational integration techniques. And normally if you need anything beyond this, it's going to be some theorem that you have to learn in some higher class to figure it out. But these guys are the fundamental. These ones, the fundamentals, these guys are the guys that are always going to be relevant. They're always going to be useful. Integration by substitution, integration by parts, integration by basic rules, integration by partial fractions, integration by trig substitution, integration by inverse trig substitution, and integration by the trig identities. These are the basics, right? The foundation. Everything else that you will ever learn about integration will build on these guys. And we are going to do some other applications of integration where we're going to already need to know these guys. However, there is a reasonable worry here, and that is, if I see a random integral on a test or a quiz or in real life, quote unquote, how do I know which one of these strategies I should actually try? How do I know what to approach? Like, how would I have seen that this guy was actually a trick and that I didn't actually need partial fractions for it, right? The guy that I had before, right? How would I have noticed that, right? I mean, if I didn't know that I was supposed to be looking for this, how would I know to have looked for it, right? This is what we're going to deal with now. We're going to deal with integration strategy. You have learned all the techniques, grasshoppers. Now we're going to learn to put them together, to have some sort of unified theory, some sort of standard strategic approach that if you see a random integral, you are going to know how to approach that integral at any given time. That is the goal for the remainder of class. Get you guys up to speed on how to approach computing integrals. All right, so faced with some random integral, right? Could be on a quiz, could be on a test, could be on a final, it doesn't matter, right? I want you guys to be able to master how you actually attack and kill an integral the quickest way, the easiest way, and more importantly, the correct way. So the strategy comes in a few steps, right? So these are the strategies. The first thing you're going to try, and the first three, you guys already know what I'm going to say. You see a random integral, the first thing that should come to mind, always the first thing, is there a basic rule? And of course, that means you should have the basic rules memorized. You should have these guys. Basic rule are the guys that I gave you in the table here. Is there a guy in the table here that looks pretty much exactly like the thing I am looking at? That is going to be the first thing you're going to think about. Is there a basic rule that looks like the integral that I'm looking at? Does this guy look like a basic rule? Can I apply a basic rule right away, right? So the basic rule, these are the guys like, does it look like an integral of x to the n dx, where my n is not equal to -1? Or does it look like a 1 over x dx? Or does it look like an integral of secant squared theta d theta, right? Is the thing that I'm looking at a basic rule, something that I automatically know a formula for? Because if it does, then just apply the formula. And you'd be good, right? So that is the first thing you want to look for. You see a random integral, your mind should immediately first go to, is this a basic rule? Now, granted, in a Calc 2 class, it is very rare that you're ever going to see an integral where all you need to do for it is a basic rule, because we want to test you on these new techniques that I'm teaching you. However, do not overlook this step. This step is actually pretty important because, as you hopefully have noticed, every technique that we teach you beyond this point is to get you back to this point. Why is a substitution necessary? Because if I substitute something, I can get it to look like a basic rule. Why would I want to do a partial fractions? Because if I do the partial fractions, I can get it to look like a basic rule. Why would I want to do a trig substitution? Because if I do it, the trig substitution, I can get it to look like a basic rule. The basic rules are your templates. There are your lighthouses. There are the light at the end of the tunnel. There are the light in the darkness. They are, you know, the avatar to maintain balance, all that good stuff. The basic rules are where it's at. Everything you learn on top of this is to get you back to a situation where the basic rules can take you home. So memorize the basic rules. This is the first thing. You want to be good at integration. The first step is to know all the rules in this table. That is step one. You are not going to be good at integration unless you do that first. Okay, so that's the first thing. Know the basic rules and then immediately try to spot them. That is step one. This is the first thing that the integral grasshopper must do. The second thing is, of course, if it doesn't look like a basic rule, you should immediately ask your question, can I algebraically simplify it to look like a basic rule? So like this integral here, it's not a complicated example. I just want to illustrate the point to you. I see an integral like that. My first thought is going to be, well, does that look like a basic rule? My answer is going to be no. That doesn't look like any of the guys in that table that Jhevon gave me. Then you're going to like, can I simplify it to look like a basic rule? And in this situation, yeah, you can. There's only one term in the denominator, so you can pretty much just divide that term into each part, right? Now, not all problems like this are going to be this simple, but this is just an illustration of this technique. So you would now simplify that, and you would realize, okay, now these all individually look like basic rules. I can apply the basic rule. Now, these look like another basic rule. This is 1 over x dx. That's what this guy looks like. Okay. And so you will be able to just now integrate them individually. So you add 1 to the power, you get x to the minus 1 divided by the new power plus c. Okay, so I froze up there a little bit. Can you see me now? Are we good? Okay, so let me just repeat what I just said. So you see an integral like this, and again, the first thing that goes through your mind is, does it look like a basic rule? The answer is no. The next thing is, can I simplify so that it looks like a basic rule? In this case, if you have one term in the denominator, then dividing that term into each part is one of the first things that you might think of to simplify. Then each individual part now will look like a basic rule. This part here and this part here looks like an x to the n rule, where 3, you can think of it as 3x to the 0. And the 2 over x reminds you of the 1 over x rule. So now each of these individually look like a basic rule, and then you can integrate them individually, right? So this is step 2. Can I algebraically manipulate things so that they look like a basic rule, right? But the basic rule is always the first thing you look for. If not, try to use algebra to simplify to get it to look like a basic rule. Third thing, if neither of these steps work, then the third thing you're going to think about is a substitution. Try a substitution. Now, in Calc 1, it's always kind of obvious when a substitution is going to work out. This is not always true in Calc 2. Sometimes there are times when a substitution can work out, but it's not obvious that it's going to work out, because in Calc 1, whenever you said u equals blah, they always wrote the problem so that once you find the du, you'd be able to see the du visually somewhere else in the function. After Calc 1, this is no longer the case. There are times when you're not going to visually be able to see the du all the time. So sometimes you have to actually just try a substitution quickly, or maybe just in your head. Like the better you get at it, the more you'll be able to do it in your head, and just see if it's actually going to work out. So for example, all of these problems right here would be ones that I would approach by substitution. And they're not guys that it would be obvious to approach by substitution. At least a Calc 1 student would not really notice that these guys would start out with a substitution. Now, of course, you can't finish them with a substitution, but the idea is for this one, and again, how would you know what to substitute if it's not obvious? The du isn't obvious. And again, that goes back to the basic rules. I know a basic rule. We know a basic rule that looks like e to the x dx. So I know how to deal with it if the e was raised to just a single variable, not the e to the radical of a variable. And so what I would do here is make a substitution to look more like that. So u equals radical x would be the right substitution. Then you'd realize that means u squared is equal to x. That makes you realize that 2u du is equal to dx. And then you can plug this into the integral and you'd realize that the integral now looks like this, which we can do by parts. Okay, so this is the thought process that would go through your head. Does it look like a basic rule? No. Can I simplify it to look like a basic rule? No. Can a substitution work? I don't know. Maybe. What would I substitute? Well, I'm going to make a substitution specifically to make it look more like a rule that I had memorized from step 1. To get that to work out, I need to make sure that this radical x in the power looks more like a single variable. So replace the radical x with a single variable, right? So that's what I would do. And you'd realize you'd end up in a much nicer situation where it's a little bit more obvious. Same thing here. You would do a substitution, something like u squared is equal to 1 minus x squared, and then you'd have 2u du is equal to minus 2x dx. And so you'd realize that you need an x here. And at first, it's not obvious where you'd get that from, but then you'd realize that this guy I can think of as x squared times x, and then this is the guy that is going to get me to look like that. So at first, visually, you're not really seeing the x exposed, but by first attempting the substitution, you now just finagle everything to try to get that substitution to work out. And oftentimes it does work out. In this scenario, we actually saw a similar situation here. U squared is equal to 1 plus x squared. Your 2u du is going to give you 2x dx. And again, seeing this here, it's not obvious, you don't really see it, but by multiplying by x over x, it gets you that guy. I would use a u squared substitution whenever it's convenient. So because of the radical here, I use a u squared because of the radical. Yeah, or you can see it by saying set u equals the square root of 1 plus x squared, and then you'd be able to just square both sides and get that. Remember, you want to do a substitution that's going to make it look like a basic rule. You don't really have a basic rule with a radical, actually. All your basic rules look like things to whole number powers. Most of them, right? Except it's like an inverse trig function or something like that, which this doesn't even look like one of those. But then you'd realize that, hey, I can get this substitution to actually work out. So that's always going to be the third thing. Does it look like a basic rule? If yes, just apply the rule. Otherwise, can I simplify it to look like a basic rule? If yes, simplify it, apply the basic rules. 3, can a substitution work? It's not always going to be obvious. So actually try it out, see what would happen after you do the substitution, and then you start from scratch and see, can I evaluate that integral? So all of these guys, we actually did guys like these already, so I'm not going to finish the problem. I just want to explain what you would look for, how you would see it, that kind of thing. So that's the substitution. Now, this is very important, what I wrote in red here, right? The above steps are always taken and always in that order. Always taken first. I should put that into the main notes. Okay, so the above steps, you always do them first, and you always do them in the order that I just told you. First, look for a basic rule. If not, try to simplify it so that it looks like a basic rule. If not, try to see if a substitution is going to work out. And remember, it's not always obvious at first glance that it's going to work out. So you are going to make a substitution based on some basic rule that you know. You just make a substitution to try to get it to look as close to a basic rule as possible. And then you're going to realize after some manipulation that it would actually work out. Now, it doesn't always work out, but it's worth actually checking, because if a substitution is going to work, it's going to be one of the easiest techniques to actually get to work. So it's actually worth the little time investment to actually consider the substitution. So you're always going to do these 3 steps in this order every single time. Every time you see an integral, you go through these 3 steps in your head in this order. Okay, now I'm going to talk about all the other techniques that we did, and I'm going to tell you when you might choose one. So the following ones are not necessarily in order of how you would think about them. They're in order of how I taught the class, which techniques I taught. So here I'm putting in quotation step 4. It doesn't literally mean it's the 4th thing you think about. The first 3 steps, you always think about them in this order, but after this, the order doesn't matter. There are going to be things that you're going to look for that I'm going to explain. And again, you would only do the following in the event that the above don't work. You always do the first 3 and try to get them to work, because if they do work, it's going to be the easiest ones to get to work. Okay. So the next thing we learned was integration by parts, okay? So this might be a 4th thing or a 5th thing that you look for. There is no particular order here. How would you know that an integration by parts can work out? Well, there are 2 scenarios in which an integration by parts would be useful, right? So one is if you have a product of 2 different kinds of functions, okay? So here, notice that you have an exponential function times a trig function. Or here, ET, or here you have an algebraic function times an exponential function. You have a product of 2 different kinds of functions, right? So again, remember, substitution cannot work, right? So of course here, this would not include something like the integral of, say, x squared sine of x cubed, because a substitution will work. I mean, the chat box is in the way here. Right, so again, we're only applying these in the event that the above don't work, right? So the substitution will work, so that is this, right? So again, for future reference, everything that I talk about after this point, you only think about it under the assumption that the first 3 steps did not work. Okay, so if the first 3 steps did not work, meaning a substitution isn't going to get you where you want, then if you notice that you have a product of 2 different types of functions, integration by parts might be the way to go. Not guaranteed, but it's a pretty good shot. Statistically speaking, this is the one that's going to take you home, right? So you see two different kinds of functions, that's going to be an option. Another situation in which integration by parts will be useful is if you look at the integral and you realize that there might be one function, there might be two functions. However, you realize that it would be more convenient to have the derivative of the function that you're looking at than it would be to have the function itself. For example, here, notice that I know that the derivative of tan inverse is going to be 1 over 1 plus x squared, and this is more convenient to have. So I realized that, you know what? It's nicer to have the derivative here than it is to have the function itself. And of course, as you would have it, if you set u equals the tan inverse and your dv equals dx, you get to a situation where you can actually solve this equation. So you can have u equals tan inverse, and then your dv equals to dx. Or you can look at the secant cubed example. You would break this up like a secant squared and a secant. And here, you'd realize that it's more convenient here to take derivatives of one part. I should put this. Convenient to take the derivative of this. And this we can integrate easy. Right? So for the integration by parts, these are the two main scenarios where it would work out. If you spot that you have a product of two different types of functions, or if you have one function whose derivative would be more convenient, or if you have two of the same types of function where you realize having the derivative of one of them would be nicer, then integration by parts might be right for you. Call your doctor today and ask if integration by parts is right for you. Okay. Right, so that's how. Speak to your doctor today. I'm sorry, I'm cracking up by my own jokes. Okay. Side effects include getting the integral correct.
Very hilarious. I get a commercial. Medicines and prescriptions.
All right.
Like Aleve,
So,
and also like Tylenol and different type of medicine commercials.
yeah. Okay, Jason appreciates my dad jokes. Okay, at least. All right. So, right, these are situations in which an integration by parts might be something you want to do. Of course, there are times when the technique would seem to be useful, but it's not. Like these guys. I'll tell you right now. So you see something like e to the x squared. I'll tell you right now, this guy has no antiderivative. Has no antiderivative. This guy, for a Calc 2 student, is literally impossible to integrate. Right? In elementary functions anyway. So no technique that we learned is going to help you with that guy. And in fact, no technique that you're ever going to learn is going to help you with that guy. There comes a point where this integral is important, or at least a definite variation of it, that we just make up an answer for it to be the answer. Kind of like how we made up the fact that square root of -1, just call it I, and that way we can get to an answer. Yeah, there's going to come a point where you're going to do that for this guy. So that guy, impossible to integrate. No technique is going to work. This guy might seem like an integration by parts will actually work. And for this one, integration by parts, int by parts would lead, you can try this on your own, but I can tell you right now, it would lead to you would end up with 0 equals 0, which is, it's true, but it's not helpful. So if you try integration by parts, whether you use the u to be the sine function or the cosine function, you're going to realize that it's not actually going to work out. By the way, for this guy, just to mention here, step 2 is what you would do. You would simplify using, there's a set of formulas called the product to sum formulas from trigonometry. So just be aware that, yeah, there's some times where you might think an integration by parts would work out, but it's not going to work out. This is going to happen. The more experience you have, the more you're going to notice when it may or may not work out. However, the above 2 reasons are the ones that you want to actually look for. So now let's look at step 5, right? Apply techniques of trig integrals. Basically, this is when trig identities can be very useful. So you see something like this, or this, or this, or even this. I actually mentioned this up here. So the simplification would be from you doing an addition, using the addition formulas for sine and cosine is one way to go about it. It's going to be a lot longer though than to using the product to sum formulas. So these are all integrals that I taught you guys how to deal with specifically. I'm not going to go over that, but this is something else you would look for. If it has trig functions and you realize applying some trig identity is going to be useful, or techniques of trig functions, do that. And that one's pretty much going to be obvious because you're going to look at an integral and it's just going to be all trig functions, okay? Another one is the trig substitution. Now, these guys are particularly useful whenever we see one of these. So you have to notice one of these in play. So you have to either see this. Must notice a form like this or that, right? And this is especially useful if one of those forms show up under a radical, but they might not show up under a radical. They can show up all over the place, but as long as you see this, you realize, hey, I can do a trig substitution. Like for the x squared minus a squared, of course, you're going to substitute x equals a secant theta. For the x squared plus a squared, you substitute x equals a tangent theta. For the a squared minus x squared, you would substitute x equals a sine theta, right? Again, make sure a regular substitution won't work. Can't stress that enough. You should be going through step 3 before you even get here. So make sure a regular substitution is not going to work before you even think about doing something like this. And of course, if you're using a definite, so these are just some things I want you to remember. If it's a definite integral, change the limits and avoid the back substitution. It's just going to make your life a lot easier. And again, the forms above are flexible. So if you see something like this, you can still think of it as an x squared minus a squared form where your a is a radical 5 and your x, quote unquote, is now just 3x plus 1, which you can make it look like an x by a substitution. Okay, so that's with the trig substitution. Okay, so the next one is partial fractions. This is the one that we started last class and we finished up on this class. This guy is applied when your integrand is a rational function, and it's very important that you realize that it is rational. Rational means, remember, ratio of polynomials. That's what a rational function is. Right? So you have one polynomial divided by another polynomial. And of course, it's very important that you realize that the denominator is factorable. If the denominator is not factorable, then it's not a partial fractions. It's something else. Chances are it can be a trig sub, but you'd have to complete the square and things like that, and we'll talk about that later. Okay, so partial fractions would be, again, substitution won't work, simplifying and reducing and getting something easier won't work. But if none of that doesn't work, what you can do is try a partial fractions. Use a partial fraction to break it up into smaller integrals. And of course, the function must be proper. So if you see something like one of these guys, we saw this already, what you would do is you'd think of this as x squared minus 1 plus 1. And then that would be 1 plus 1 over, say, x minus 1 times x plus 1. And then this guy you can actually break up into this guy, which in this scenario you can actually do the cover up method to get to the answer easy. Cover up x minus 1, plug in 1, you get a half. Cover up x plus 1, plug in this, you get minus a half here. Right? So that would be the way to go. And each of these now look like a basic rule. We're now back in step 1. This one is going to be the same thing. I would just think of x squared plus 1 minus 1. This is going to be the integral of 1 minus 1 over x squared plus 1. And this guy, you'll notice that that is the arctangent integral. Right? So sometimes you realize by reducing the fraction, you don't even need the partial fractions afterwards. Sometimes you, even after reducing, you might need it. So you'll notice that you may or may not need the partial, you may or may not need partial fractions after reducing. So you always make sure that you're in a reduced version before. So here, may not, I didn't actually need partial fractions. Here, I actually did at the end of the day. But the thing is to know what to look for, right? So I see a ratio and substitution is not gonna work because I'd want to substitute the denominator, but it doesn't work out nice. By doing a substitution, I'm gonna get something much uglier, introducing radicals and all that sort of thing. 8, the Weierstrass substitution. This works out when you have rational functions that just have trig functions in place of regular functions. So for example, technically speaking, the one that we did over here, you could use a Weierstrass substitution on this guy. Of course, it's actually harder than going through a regular substitution partial fractions, but you could actually do that. This is the kind of integral that you would use a Weierstrass substitution to figure out, assuming that the regular substitution didn't actually get you anything useful. So again, I skipped that. I recopied the links here again if you want to actually check them out. So we're not covering it in this section, but it would be one of the fundamental techniques. And that's basically it. I left some space. I left some space here. What?
Let's go up, especially with the partial fractions. Like, you know, what happens? Why isn't it like, you know? It's no, like, just go a little down.
Like that?
Yeah. In this part, you see the half over x minus 1 subtract half over x plus 1.
Yeah.
Shouldn't the halves be switched? Like, you know, a equals, like, you know, positive a half and b equals negative half. Like, you know, shouldn't it be like half ln absolute value of x plus 1 subtract half or ln absolute value of x minus 1?
No, the signs are right. I just double checked it. Use the cover up method with your finger on the screen and you'll see that it's right. Because the guy that goes on top of the x minus 1, it happens when you cover up the x minus 1 and plug in x equals 1. You would actually get a positive a half. And then if you cover up the x plus 1 and plug in x equals minus 1, you get negative a half. So the signs are right here.
What happens if the a's and the b's get switched?
Well, if you went the a and the b method and you went through the method, you'd actually get the right guys. If you wrote this one first, you would actually get a negative value for the a, and if you wrote this one second, you get a positive value. If you go the a and the b way, you'll get the right answer eventually. So I wouldn't worry about that. Whether you're using the cover up method, you'll get the right signs. I think you got mixed up because maybe you wrote these guys in a different order, but the signs are right here. Okay, but that's when you do a partial fractions. You have a ratio of polynomials. First, make sure that you reduce it. So if the highest power on the top is greater than or equal to the highest power on the bottom, you need to first do a reduction. Either do algebraic manipulation to simplify it, like add and subtract something convenient, or multiply and divide by something convenient, or do a long division if it comes to that, if you can't really see how to maneuver things. you might realize sometimes that after doing the reduction, you don't even need the partial fractions at the end of the day. But it's possible that even after doing the reduction, you still have to finish off with the partial fractions. But either way, you would think to do this, assuming that a regular substitution or simplification will not work, and you have a ratio of polynomials where the denominator factors. So that's when you would actually think of partial fractions. Weierstrass substitution, we're skipping that. If you're interested, go here to check those out. And I was going to mention some stuff here, but I don't know. Should I do it? So the Weierstrass substitution is this. You would actually substitute u equals the tangent of x over 2, i.e., notice that you're substituting x equals an inverse tangent. So this is if you have the integral of f of x dx, and f of x is a rational trig function. Right, which means it looks like a ratio of polynomials, except instead of x's, you have trig functions in those places. Then this substitution can actually be quite useful, because now if u is equal to tangent of x over 2, your du is going to be, well, let me rewrite it differently. Then this means your x is going to be tan inverse 2 times tan inverse of u. So it's not tan inverse of 2u. I just did the algebra in my head incorrectly. No one corrected me. So it's 2 tan inverse of u. But then your dx would be 2 over 1 plus u squared du. Then you'd realize that, okay, I can draw a triangle here, where if the angle is x over 2, the opposite is going to be u, the adjacent is going to be that, this is going to be the square root of 1 plus u squared. And so this means you can figure out what your sine of x is. Sine of x is going to be 2 sine x over 2 cosine x over 2. This is going to be 2 times opposite over hypotenuse times adjacent over hypotenuse. So you'd be able to replace any sine function that you see. You can replace it with 2u over 1 plus u squared. Similarly, if you have a cosine function, this is going to be cosine squared x over 2 minus sine squared x over 2. And so that's going to be 1 over 1 plus u squared minus squaring the sine function, u squared over 1 plus u squared. And so you would get that a cosine function you can think of as 1 minus u squared over 1 plus u squared. And once you find out sine and cosine, you can actually figure out all the other trig functions. And so just to give a quick example, suppose I wanted to figure out the integral of secant. So remember I told you guys that I can give you another way to figure this out. The Weierstrass substitution was the way. What I would have done, instead of figuring out that you had to multiply and divide by that random thing, you could first rewrite it as that, then replace the cosine with 1 minus u squared over 1 plus u squared, then replace the dx with 2u over 1 plus u squared du. This is actually going to give you 2 times u over 1 minus u squared du. This you're going to realize is minus 2 ln. It's actually going to be just minus ln. Let's see. This is actually going to be minus the integral. This is actually going to be minus ln of 1 minus u squared plus c. And when you plug in this, you'd realize that this is going to be equivalent to 1 minus cosine x plus c. Apply some trig identities and you'll get here. Right. So here, instead of seeing from scratch that you have to multiply and divide by something, by doing a Weierstrass substitution, you can actually get to the answer constructively. Okay. So here is an example from the trenches that I would like you guys to go through with me. Example from the trenches. So this was a student in battle. They asked me about this even today, and I shot them an email, and I actually met up with them in office hours, and we discussed this problem. So they don't need to respond, but I'm actually going to throw out this question to the class. You saw this integral. Based on everything that I've been telling you, based on everything that you've practiced, how would you actually approach that integral? Right. So I'm going to share the email response I had, and maybe we can discuss it afterwards as well. But I'd like to know what you guys think. So there was an integral of x minus 2 divided by x squared plus x plus 1. So there's this random integral that showed up while they were doing another problem in the homework. And they're like, I didn't know how to deal with it. And we dealt with it. So, all right, go. Remember your training, grasshoppers. Go through the process. Actually, give me some suggestions on how to apply it, how to fix this. And I copied my email response here. I just want to see if you guys are thinking like I'm thinking, or maybe you guys are thinking of something else. All right, so we're thinking of U sub, all right? Some people are thinking of rational roots. X squared plus x plus 1 does not factor. You don't actually need a rational roots theorem here because that's just a quadratic, right? The rational roots theorem is useful when you have something that you don't really know how to factor. Like it's like a cubic or a quartic or some higher degree polynomial where you don't really have a trick. I mean, when it comes to quadratics, we know a lot of techniques to factor quadratics. You wouldn't use a rational roots theorem here. So that's not really what you would do. We don't need that. X squared plus x plus 1 does not factor. That is important to note, but yeah, so we wouldn't need the rational roots. Now, someone else thinks of a substitution. Now, would a substitution actually work? So here's the thing. If we did a substitution, what would have happened? U equals x squared plus x plus 1. Our du would be 2x plus 1 dx. And we don't really have a 2x plus 1 dx. All right, so now these things should separate into two different integrals. Okay, so how would you separate them? Give me ideas on how to.
Yeah, it would be x over x squared plus x plus 1 minus 2 over x squared plus x plus 1.
Oh, so you want to just break it up into this?
Yeah. Yeah.
Okay, and how would that be useful? Okay, and Natalie seems to agree. That's what she thought. Now, is that useful? Can you now do the first and second integral separately? Because what would happen now? So, okay, I kind of like where we're going with this, but breaking it up into two parts is going to be, it is what I thought of doing, right? So I immediately just responded by email and typed this out. And I made a little typo because I just was responding off the top of my head, but I'll discuss that later. But yeah, splitting it up is actually what I would also do. The thing is, I would not split it up in this way. This is not a nice way to split it up. So remember, grasshoppers, what do we want to try to get to work out, right? It would be nice, I would say, for the substitution to actually work out, wouldn't it? Now, what would I need to get the substitution to work out? So think of that, keep that in mind. If I wanted to force a substitution to work, how would I break this integral up to force that substitution to work? This is not going to force that substitution to work, because making a u equals the denominator of either of these guys, then the numerator is not going to cooperate. So this is correct, but it's not actually useful here. You can complete the square for the denominator. Fuad is pulling out the big guns like tabular integration. I feel like this isn't the first time Fuad said that. He's like, you know what? This is going to be right eventually. I'm going to just keep suggesting tabular integration. Like, there's going to come, the day shall come when I say tabular integration, Jhevon's going to be like, yeah, that's actually right. I'll get you, Captain Planet, I'll get you. Okay, so completing the square of the denominator isn't a bad idea. At this point, it is a little bit premature. All right, so there's a little activity I want to do with you guys a little bit later, so I want to get to move on. Here is my actual response to the student. So I saw this and that's gonna, let me move everything all at once. So as you can see here, I redacted the name to protect the innocent. Okay, so here's how I would go through it. And so the denominator does not factor. So whenever the denominator does not factor, completing the square is something you should immediately be thinking about. So kudos to whoever suggested completing the square. Whenever your denominator does not factor and you realize that you have this kind of quadratic thing, maybe this is, right? And you have like a quadratic. Completing the square is going to be useful because what's going to happen is you're going to realize that, hey, maybe since it doesn't factor, I can't really do partial fractions. Maybe what I can do then is eventually get it to look like an x squared minus a squared, or an a squared minus x squared, or an a squared plus x squared. So completing the square is something that you would think whenever you have some sort of rational function where the denominator does not factor, right? So remember, partial fractions comes into play when the denominator factors, and it's nice. Completing the square is something you might think about otherwise, assuming that a substitution is not going to work. However, in this situation, I want my substitution to work. And notice that the substitution here, my du, if I make the coefficient of x 1, which is going to be useful because the coefficient of x is 1 in the original problem, it's 1x minus 2. I realize that x minus a half is a guy I'm going to want. So I'm going to split this guy up in such a way that x minus a half, as you can see here, is a part of the numerator. So I break this up into two fractions where the numerator of 1 is x minus a half. Now, of course, the other one this should be 5 over 2, but somehow, you know, me and arithmetic. I typed 3 over 2 here, but that should have been 5 over 2. So what I would do is I would realize that x minus 2 is actually x plus a half minus 5 over 2. And that part reminds me of the substitution part I have here. So the better way to break this integral up is into two parts like this. Now what's going to happen is the first part is going to be something that I can do with substitution. What about the second part? Now the second part I can't do by substitution, but that's where I realize I can do something like complete the square in the denominator and try a trig sub. However, in this case, you don't even need a trig sub. So here, let's you're going to realize at the end of the day, especially if you're really good at algebra and algebraic simplification, you ended up not needing the trig sub afterwards because you don't want to do a trig sub when you don't have to. So I saw this. My first thing I wanted to figure out is, well, that looks ugly. It's not a basic rule. It doesn't simplify because I can't factor the thing. Yeah, I can complete the square, but yuck, that's going to give me a trig sub. However, if I wanted a substitution to work, is a substitution going to work, right? So that's what's going through my mind at this point. So at this point, I'm like, okay, I'm going to break it up into such a way that I can force a substitution to work. Right? Now I realize a substitution is going to work on this part. And then I would end up with this half here giving me ln of x squared plus x plus 1 times a half. Right? And that's this side right here. Now for this side right here, now it's when I start thinking, oh, let me try to complete the square. So I'm going to start, oh, like here, remember, the easiest way to actually break things up is to introduce what you want and then correct for it later, right? So I know I wanted x plus a half. So what I can do is I can just take x plus a half and minus a half. So this is going to give me x plus the half minus a half minus 2 is minus 5 halves. And so that's how I decide to break it up. So again, I just introduce the term I want and then correct for it afterwards. It's like an add and subtract kind of thing. That way I can break it up into this, which is very convenient for a substitution. To deal with this guy, I would now go and complete the square. So this is now like a 5 over 2 over, this is going to be x plus 1/2 squared. I think it's plus 3 over 4. And at this point, you could do a trig sub. So at this point, you could do a trig sub. You could set x plus a half equals radical 3 over 2 tan theta. And that would allow you to do that integral. Or you can just do a little algebraic simplification. So you could realize that, well, I can factor out a 3/4, I can factor out a 5 over 2, and I can factor out a 3/4 from the denominator. And I would be left over with 4/3 x plus a half squared plus 1. Then I can bring this 4/3 inside the square. So this is now 5 over 2 times 3 over times 4 over 3. Keep, change, flip. And here I bring the 4 over 3 inside. That's going to be 2 over radical 3. That. plus 1. And then at this point, I can do a substitution. U equals 2 over radical 3, x plus a half. Your du is going to be 2 over radical 3 dx. And so now this whole integral is going to become 5 over 2 times 4 over 3 times radical 3 over 2 times 1 over u squared plus 1. And that guy we can integrate easy. So the integral here is going to just be the integral here. And so this becomes 5 over radical 3 times the tan inverse. So this is going to be 5 over radical 3 times the tan inverse of 2 over radical 3, x plus a half. Plus c. Then add this to the other part. And that's a tough problem, but I believe this was from the homework. But this is how you're going to finagle things to actually get them to work out. Now, something like this, you're not going to get as difficult as this on a quiz or a test. But if you can get through a problem like this on the homework, then you shouldn't have to worry about a quiz or a test. And you shouldn't have to worry about actually running out of time on a quiz, right? And it's not so much math instincts. It is just really being good at going through these steps, the same steps that I gave you, right? Once you really get good at them, you're going to know what you want to look for. You're going to know how you want to manipulate something to get a certain strategy to work out, right? So once you have those steps that I mentioned, and you have the algebra skills to pull it off. So you have to be able to realize that, oh, I can get this to look like that by doing this, or just manipulating it this way. I can add and subtract, or I have to do the rational roots theorem and I'll get into this situation. Once you can do all that, it's going to be very useful. Okay, so this is one from in the trenches. I thought I'd share that with you, because this is a very challenging problem, but it has a lot of lessons for us, like how you would actually go through and approach a difficult problem. So that being said, I mean, I think it's running a little late to do the activity now, even though it's going to take another 5-ish minutes or so, but I think I want to wrap up. So let's actually stop here. We'll save the activity for next time. Yes. Hello?
Jhevon?
Yeah?
Before we leave, actually, when are we going to have our next quiz?
On Monday.
Monday?
Yeah. So have a quiz on Monday. It'll cover everything we did this week. So pretty much for the quiz next week, just know all about integration. So pretty much you'd want to study this lecture, make sure you know the steps and the strategies, then do a bunch of integral problems, practice all your, practice the homeworks up to I want to say we're in 8.7 or something like that. The partial fractions was, yeah, so cover everything up to all the basic integral formulas, which I think is 8.5 or 8.6, maybe 8.7. And that should have you prepared. So I don't know if your textbook has a chapter on strategy, but it's important to know strategy. So that's what I just went over with you guys. Yeah, so know everything up to 8.5, it looks like. Okay, so we're gonna stop there. So you're going to go this weekend, memorize the strategy, learn the strategy, really practice applying the strategy. And again, like with anything, you have to be aware that learning it for the first time, doing it for the first time, it's going to be frustrating. It's going to be hard for a lot of you, but you need to push through. Your salvation is on the other side. Push through. Every time you do an integral problem, force yourself to think through these steps. Before you know it, you're going to realize it's going to become automatic. It's going to start thinking, you're going to eventually be able to see it. You're going to get to the point where you're going to now know how to strategically skip over steps in your head. And you can immediately just look at something and know, oh, that's going to be a by parts. Or I can look at it and know it's going to be a partial fractions. I can look at it and know trig sub is how I'm going to do it. And you can know right away. But at first, you take baby steps. You do the hard thing. You go through the steps carefully and slowly. Think in a certain order. You're actually training your brain. Eventually, your brain will be able to get through these things a lot quicker. And you'll be able to look at integrals and be able to tell exactly what the approach is going to be, what's the best way to get it to work in the shortest amount of time. And I'm actually going to do an activity with you guys next week that's going to help with this. But for now, just practicing these strategies and getting through the homework and doing a bunch of problems over the weekend should prepare you for the quiz in either case. All right, so okay. All right, so we are going to wrap up there. As always, I'll post the video and a PDF of this online. But for now, have a good weekend, guys. Have fun studying, and I will see you guys in the next one. All right, take care. Bye-bye. Ciao.